Okay, so now let's take some results from topology that we need. So let's recall that from your algebraic topology course that for X, which is just the surface of genus G, this is not a question of complex structure now, it's just a pure question of pure topology, right? That's just what it is. As a surface, I mean, it's orientable compact surface of genus G. I mean, all these groups that I mentioned are completely can be calculated. Of course, we said H0 of X, Z is isomorphic to Z. H1 is what we need. This is isomorphic to Z to the power 2G. And H2, again, not needed, I don't think so. This is also isomorphic to Z. Okay? So H1 of X and Z, you can think of generators for this. For now, you can just take these generators.
Genus of X?
Sorry?
Genus of X? Oh, it could be anything. Sorry, yeah, like that.
Oh, yeah, anything, yeah. In this case, it's 3,
Okay.
but it could be anything. So in this case, you just take these cycles around each loop, each hole, basically. So you have A1, B1, and then you can take A2. For now, this is good enough, but we'll choose something more refined later. A2 and then A3, B3, and so on. Okay. So this is generated by cycles A1, AG, and B1, AG. I mean, this is just to give you some intuition, but it's not so important. Okay, so as I said, now we want to define this map, this pairing from H1 of X and Z plus omega of X to C. This is basically integration. So, so if you have a homology class here, C, and a holomorphic one form omega, right? You map it to.
What are the generators of H1X?
Sorry?
What are the generators of H1?
H1 of XZ?
Yeah.
These are these. What is the question?
So what are the generators? Generated by cycles?
Generated by cycles A1, AG, and B1, BG. There are 2G cycles, which generated. Yeah. Because you need cycles, right, to generate. They have to be in the kernel of the boundary map, right? So this is integration over C of omega. Okay, so there are a few things we have to care here first. Okay, first of all, I mean, this C is only a class, right? C is just a class. Is not a curve really. I mean, it could be homologous to other things as well, right? So why this depends only on the class, not on C itself. So in other words, so the question I'm asking is why this is well defined, basically. Why is this well defined? I mean, you have to, anyone gives you the definition like this, you have to ask why this is well defined. So why this is well defined is hinges on two facts, right? First of all, this omega, which is a holomorphic one form, is Durham closed. So the proof hinges on two facts. I mean, omega holomorphic, I have done this before actually, but I do it now. Omega holomorphic implies that d of omega, well, this is the Durham differential, is equal to 0. This is the Durham that appears in Stokes formula, for example, right? So why? Well, I mean, it's quite easy to see because, so here's a proof, right? Okay, well, what holomorphic means, locally omega is, we can write locally, omega can be written as f of z dz, locally. Only locally you can write it like that, right? Okay, now you want to differentiate this and show that its Duram derivative is zero, right? So what is the Duram of f of z dz? What is it? Well, this d is, so you have to apply Duram to this and then put, okay, so basically this is, I can just say, so what is the right way to do? This is d of f of z, I'll just say it like this, exactly, times dz. First of all, this is the definition of the Duram in general, right? You know, because d of d is zero, so this is, you have to take d of this coefficient only, which is a function. Now, what is d of f of z?
F prime dz.
Huh?
Prime dz.
Oh, what, yeah, so yeah, this turns out to be actually equal to f prime of z dz, and then you are wedging with dz. This is zero, so this is zero. But the only question is why, honestly, this is f prime of z dz. Maybe a little bit of argument is needed there. So I'm asking why Duram of f of z is equal to f prime of z dz. I mean, here is complex differentiation. That's a different story. You see, it's a complex derivative. Right? So the reason is that d, we can just write it as what? Del plus del bar is a sum of two differentials, del plus del bar, right? Plus del bar. So d of f of z, if you consider this only as a complex valued function in two variables, is going to be equal to del plus del bar of f of z. Now, what is that guy? This is del of f of z dz. Now, I don't know. I mean, I just write it as d dz. I mean, I don't know how to write it. I just write it d dz. Yes. Yes. It's not good notation. No. I should write. So I just need a good notation. Yeah, plus. Okay, so let me put it this way. Maybe this is better. This is equal to d dz of f of z. Oh my God, this is bad. Plus d is z bar of f of z. I don't like this at all, but okay, this is zero because this guy is holomorphic. This is f prime of z. dz. So I'm a bit ambiguous here. You just fill in the details, okay? So that. So my notation is not perfect here, but you will fix it. Yeah.
I just wanted to ask, so this map, like, we want it to be a perfect pairing, you said, right? Is that what you're trying to
I
define?
never used the word perfect today, actually.
Oh,
Maybe when I said the weather is perfect.
Periodic pairing.
Huh?
Periodic pairing.
I said it's a period pair.
oh, I'm sorry, I'm just, yeah, no, sorry, that's the brain fart. So what is the condition on that map? For it to be a period pair? Like, is it just any map of that form, or is there a condition?
Right, no. Okay, I will tell you why this is called periods, because these are periods of these differential forms. But yeah, that's yeah. So that's is that
Yeah, I just wanted to, what is the condition that you need to check for a map to be in period pairing? Like,
oh, there is no general concept of
Oh,
it.
it's just
This
that-
is the period
yeah,
pairing
this is
for
the-
Riemann
okay,
surfaces.
okay,
Yeah, you can define it for general varieties, algebraic varieties in general. But then in that case, you have to integrate over higher dimensional cycles.
Yeah.
And then you have periods of forms in general over higher dimensional cycles. Basically, it's integration. There's
Okay.
nothing.
Okay.
So yeah, okay. So now actually, no, that's a good point. Actually, I understand your question is what is a period in general?
Mhm.
Yeah, that's an excellent question. The period is just the integral of algebraic differential form over an algebraic cycle.
Oh, okay.
I mean, this is general. I mean, in this case, we can just define it with continuous paths and stuff like that, but that's okay.
Yeah.
So your question, yeah, really is important. Yeah, indeed. Yeah. So when someone utters the word period, don't be afraid. It's just integration. It's calculus. It's nothing more than that. Okay.
Cool. Thanks.
Okay. So now, but we can do nice things with it. Okay. So I have to fix that notation over there a little bit, but this is definitely closed, Duran closed. So then the Stokes formula shows that this is well defined. Okay. So then the Stokes formula. Okay. So I just say since C is a cycle and omega is Duran closed, Stokes formula shows that this pairing is well defined. The pairing is well defined. Okay, I just leave it at that, but if you want, I can explain after the class. That's that follows from that. Okay, so then I just turn it upside down, not upside down, maybe dually. I'll just write it like this then. So what we can do now, I can consider the same map in the following way. So if you want, you can call this period pairing. Yeah. So basically then same map dually can be written as, so now we have this map from H1 of X and Z to omega star of X, right? This is, by the way, as I said several times already, this is home of omega of X and C. Because what is this map? I mean, you just have a cycle here. I mean, a homology class, you send it to this the thing that sends omega to integral of omega, to this linear functional over omega of X over C. Right? Okay. So this is called the period of this differential form with respect to this cycle C. Then what we can do, now we can look at the image of this map. Now this map, I don't have a name for it. Actually, I'm not sure I should name it. Maybe I'll call it, but I just don't want to introduce an unnecessary name. Maybe I call it P. But this is a very bad idea, I'm pretty sure it's not. Because nobody uses this P. Okay, so So let's see, okay, so now the question is image of P in omega star of X is a lattice lambda inside omega X star. This is called period lattice. The period lattice.
Omega star of X different from omega X star?
Sorry?
Omega star X and omega X star are the same thing?
Yeah.
Okay.
Oh, yeah, okay, so yeah, okay, good, yeah, okay, so, maybe I should actually put it here, you're right, no. Good point, yeah. I put it here. Are you happier now? Excellent. Okay, so now there is something to be checked. Okay, so here is a lattice, you see, H1 of X and Z is isomorphic to Z to the 2G. So it's just a discrete object, right? It's really a lattice in some homology space, or actually it's an abstract lattice, Z to G. But now we want to say that under P, it goes into omega X star, and this image is a lattice actually of the same rank. Is a lattice of rank 2G. So there's something to be checked now. So lambda is a lattice of the same rank 2G. So this I have to prove later on using some special basis and some arguments. So maybe I have to define, I have to use even a little bit of Durand theorem, a little bit of Hodge theory, but that's not very difficult. So of the same rank 2G in, okay, so let me look at the proof later. Okay, so if you accept that, then so we have a lattice lambda of rank 2G into this complex vector space, which is, by the way, isomorphic, but not in a canonical way, to CG, which is R to the 2G. So you have a lattice of rank 2G in this real space of dimension 2G. And you take the quotient, and this quotient is the Jacobian of X. So the definition is that Jacobian of X is the G-dimensional this is the complex dimension, complex torus. So this complex torus is, okay, I just write it here. So the notation is Jac X. So this is by definition equal to omega X star divided by lambda. So it's a complex torus. Its complex dimension is G. So it's a group. Okay, so it has a lot of other properties. So it's an example of an abelian variety. So let me write something maybe a little more general in this case. Any question about the definition? Okay, so now let me just make some comments here. Okay, so Jacobian of X is a, G-dimensional complex, compact actually, because it's a torus, compact, complex Lie group. It's a Lie group in the category of complex manifolds. So, okay, in algebra, people call it algebraic groups, but this is a big object. Lie group in the category of complex manifolds. And then, of course, this is an abelian thing by definition, by our construction is abelian, because this guy is abelian, and we are dividing by this. This is abelian. So, is a G-dimensional abelian. But actually, it's redundant. I don't even have to say this is abelian. So redundant to say that, because people can prove that, and in fact, it's not so difficult to show that any compact complex Lie group is necessarily abelian. And that's not what you have with real Lie groups. There are beautiful non-abelian compact Lie groups, like SUNs, SONs, a lot of these groups that are non-abelian compact. But in the complex analytic category, any compact Lie group is abelian. So I don't even have to say that, but in this case, it's by construction abelian. So Jack X is an example of an abelian variety. So abelian variety exactly is what it is here. I mean, it's a compact complex Lie group. Compact, complex, hence abelian Lie group. Okay. So we have this. Let's see what it is now. Maybe compute it in at least in two cases that we can easily compute. Any question about this?
Yeah. So if I have X a modular curve on genus at least 2, can I construct the stable Jacobi map algebraically without integrals?
I'm not sure. I'm not sure. I don't know. Yeah, it's maybe. I mean, I know residue theorem can be proved without using integration.
No.
Because the proof that we gave used integration. We use the Stokes formula to prove the residue theorem. But you can prove residue theorem, and then that's actually important when you try to prove Riemann-Roch for curves over arbitrary fields. That proof is the one that you need. In this case, I'm not sure, but this is a good question. But now let me give you some examples. Any other question? So why did you ask that question, though? Just
I like algebra.
Yeah, sure. Of course, yeah. No, absolutely. Yeah. Sure. I mean, a lot of this theory goes in the algebra category for sure. I mean, it's beautiful algebra category. I mean, it's very important, very, very important. By the way, we still don't know which abelian varieties are Jacobians of curves of Riemann surfaces. This is a famous Schottky problem. Which abelian? So they have to be polarized. There is some condition called polarization, but it's still which polarized abelian varieties are Jacobians of curves? We don't know. It's an open problem. You can try. But then, okay, so we'll see a little more of this. So for now, let me just do two trivial examples, but nice, anyhow. Okay, X C hat. What is Jacobian of X? That's the most important example everyone should do, right? All the time. You check everything that you know against this trivial example. So what is Jacobian of X? So you have to take omega of X, the star, divided by period lattice. But what is omega of X?
Rational.
It's all constant functions because we.
Oh, yeah.
They are not functions. They are one forms, and they should be holomorphic. What do you know about holomorphic one forms on C hat? There is none except 0. So this is 0 star divided by, you don't care what lambda is. This is 0. Don't even burn your brain on that. So this is 0. So it's a point, it's a zero-dimensional thing. It's just okay. I mean, this was one of the, I believe, assignments. I think to show that any holomorphic one form on C hat is 0, and you can prove it directly. That's not difficult. So example 2, x equal to C over lambda, genus 1. So what is this?
I think it's itself.
Jacobian of C over lambda. What is it? Okay, so we have to look at holomorphic one forms on C over lambda. Well, there is one which is dz. Our friend dz is a holomorphic one form on this, and any other holomorphic one form is going to be multiple of this by some holomorphic function, and there are no holomorphic functions except constants on compact spaces. I mean compact Riemann surfaces. So then this is just C dz star. Now what is the period lattice? Which is inside C dz the star. So we have to take 2 cycles in the torus and integrate dz over those 2 cycles, right? So I have these 2 cycles, integral dz over C1 and integral dz over C2. So what are C1 and C2? I mean, the obvious cycles are the cycles that are defined by the original lat. Oh, by the way, I have to, so this is a bad notation, sorry. I have to use a different notation because it's not clear that this lattice is the same as this lattice yet. So I just say okay. So this is the lattice. So this is the period lattice. Just to distinguish. I mean, we will prove now that this is actually the same as this one, but for now, I just choose a different notation. You see the notation. Okay. So now, what are these guys? Well, these guys are the following numbers. Just define you the lattice. So basically, you have this original lattice lambda inside C. Okay. It's not a lattice. Okay. So now we have got omega 1, omega 2. Lambda was equal to, C omega 1 plus C omega 2. So, Z, I'm sorry, yes, Z. That's terrible. Okay, yeah. So when you do that, so when you go to the quotient, they give you 2 cycles in the torus, right? This is C1, and the other one, coming from omega 2, I call it C2. Okay, I mean, if you integrate this, dz, over C1 is actually, so, I mean, this dz is a perfect differential. You have to subtract from this end to the other end, right? So this is just omega 1. And the other one, integral dz over C2 is omega 2. So the period lattice is the same as the original lattice. So, I mean, I will equal C And if you identify C is a star with Z, with C, I mean, there's a canonical identification because there's a canonical basis in this space. So in the dual, so I can canonically identify C is a star with C. If you do that, then this lattice is really the same as this, under this isomorphism. Under this isomorphism, this lambda is equal to C. Okay, so then we have got this is isomorphic to C over lambda again. So the Jacobian of
C
a,
over C.
sorry,
Is it C over C?
C over Z?
C,
C?
because
No.
the lattice is C.
Huh?
The lattice is C.
The lattice is not C.
Oh, but no.
No, C is the star is C.
Right, and what's the lattice?
The lattice, oh, this is bad. I'm sorry. That's what I meant. Yeah, good. Yeah. Thank you for being attentive. Okay, excellent. So this is really what we want to do. So the Jacobian of the complex torus is the same as the thing. So they say Jacobian of elliptic curve is the same as the curve itself. So Jacobian of the complex torus. I mean, okay, so Jacobian of, I mean, maybe I have written this several times already, but let me write it. Jacobian of C over lambda is isomorphic to C over lambda. And that's the only case that this happens, because if you go to higher genus, the Jacobian picks up higher dimensions, right? Is as a complex space, as complex dimension G, but the Riemann surface always is one-dimensional as a complex manifold. So they start to diverge. However, we can define a map. This is the Abel-Jacobi map. X into, so this is the next step now, Abel-Jacobi map. So people use different notations. I think I use A in honor of Abel. Goes from X to Jacobian of X, which is, let's not forget, omega of X star divided by, how do I do that? Divided by lambda, by period lattice. You know, oh. Okay, so this is the period lattice. So to define this, we fix a point, P0 belonging to X. So we have to fix this point. There's no way around it. We have to fix a point P0. And we define A of P. So I want to define something that is an element in the dual modulo lambda, right? So I just have to define its value over omega, right? So omega is omega belongs to omega of X. I just define it to be integral from P0 to P omega for all omega belonging to omega of X. Now, I would consider this as an element in the quotient, so I just take its class in the quotient. Okay? So let's see what we did. This is, so again, don't let Abel-Jacobi map scare you. This is very simple. This is just integration. That's the most elementary thing you can do. You just integrate a differential form along a path. That's it. But it has amazing properties. So let me just tell you what I did. So this is your surface again. You fix a point P0, and pick any point P, and now I said integral P0 to P. So there is a hidden ambiguity there, right? Along what path? That's a problem. Along what path? So you can go here, you can go here, you can take this path here. And in fact, along any path. So integration can be performed along any path. Because you are dividing by lambda, by period lattice. The difference between two things is in the period lattice. Since we don't want to define something in omega of x star, it actually doesn't exist such a map. If you divide by the period lattice, it's well-defined, and only then it's well-defined. To kill the ambiguities, right? So let me write it along any path, since we divide by lambda, which is the period lattice. Do you see this? So let me is that okay? So let me draw a picture. That's the easiest way to prove this. Or I just draw a picture. So here is here is our thing. So we have P0 and we have P. So you choose one path, I choose another path. So I just call this C1, call this C2, and I want to take integral over this path C1 omega, and then I want to see the difference between this omega over C2. But the difference between the two is just integration over the chain C1 minus C2, which is a cycle. C1 minus C2 is a cycle. So since this is a cycle, so this belongs to the period lattice. We are integrating in one form over a cycle, and this is exactly the definition of the period lattice, right? So by dividing by lambda, you're okay. No problem. But if you don't divide by lambda, of course, this is not well defined. Well, there is still this issue of P0, initial point P0, which is okay. I mean, we will handle that. And then, okay, so, and then we have to extend this Jacobi map to the divisors on X. Okay, so let me write it. So, I'll just tell quickly, but then we'll do it on Tuesday to finish this. But okay, I mean, any question, by the way?
So,
Yeah.
P naught is any point that is not P.
Sorry?
Is-
No, it could be P. P could be P naught. I mean, if P is P naught, actually Jacobi map goes to 0.
Oh, okay.
That goes to the origin to the 0 of the group, yeah, in the image. That's okay.
And here, this is notation is using the class is sends omega to this integral.
Exactly. I mean, I want to, any point on the surface gives you a linear functional, which is the linear functional that on this one form gives you this value.
I get it. This is the notation.
I hope it's not confusing now. Because notation is unambiguous, actually. You see, AP on omega. Okay, maybe this notation you mean confusing.
Yeah,
P0 to P. Yeah. So this is what everybody writes, but it's understood that you're integrating over a curve from P0 to P. And that doesn't matter which curve you take, which path you take, because you're dividing by the differences in the period lattice, so you divide by. Okay?
Yeah.
Very good. So, okay, so we have to finish now, but the next step is we define this. So let me write the upcoming thing. So then we shall extend, and that's not difficult actually. I still call it A from divisors on X the Jacobian of X. And then we will prove that A0, if you restrict it to divisor, zero divisors, I mean 0-degree divisors, to Jacobian of X, yes, this is actually turns out to be isomorphic. So isomorphism, this map, this over Jacobi map, gives you a one-to-one correspondence between 0-degree divisors and Jacobian of the curve, the Riemann surface. And then yeah, I mean, well, I mean, this is part of the package. I think if there is time, I will also give an alternative description of Jacobian in terms of symmetric powers of the curve, and then which was already known to Abel, by the way, amazingly. And yeah, so okay. So the first application after we prove this is that there is so we just classify all complex tori. We'll see that actually C over lambdas are all complex tori, and then we'll see. So there are other applications, but like Abel's theorem and all these things. So okay, so I think I stop now, and then we just. If you have questions, feel free to ask. Yes.
Oh, when is the project